Hi, since we talked about continuity being an important property in a calculus course, I thought I would just do two more advanced problems, a little more advanced, so that maybe you get a little better understanding. So here is a function, fairly complicated looking function, and we'd like to know where it's continuous. And that is actually a fairly easy question. We know that the numerator is a continuous function. It's a polynomial, and so is the bottom. Therefore, we know that the whole function is continuous everywhere except possibly, except where the denominator is equal to 0, and that's going to be at x equals 3 and negative 3. So right away, we can say this is continuous for all real numbers not equal to negative 3 or 3. So really the difficulty of this is to know what's happening at negative 3 and 3 to cause the discontinuity. Now, if we plug in 3 to the numerator, we get 27 minus 21 minus 6. So we get 0 over 0. So that's an indeterminate form. So we really, without a little more analysis, we don't know exactly what's going on. If we plug in negative 3, I get a number in the numerator, a negative number, and in the denominator I get 0. So as you get close to negative 3, what we see is the numerator is getting close to some number and the denominator is getting really close to 0, which makes the whole function value get really large or really, really small. It's going to infinity or negative infinity. So we know at negative 3 we have an asymptote, and it's x equals negative 3. Now, it's a more difficult question at 3. We're thinking because we have 0 divided by 0, maybe we have a whole, but we're not sure unless we take a limit and see if really, as x approaches 3, we're coming together at the same point. So, I'm going to take the limit as x approaches 3. And in order to do that, I have to do some algebra. Well, I'm going to factor the bottom fairly easily. This is where this makes this a little more difficult because the numerator is not so factorable. So this is more of an algebra thing than a calculus thing, but do we remember how to factor that? Well, since we know that 3 is a root, we know that x minus 3 has to be a factor. Now, to find what the other factor is, what we can do is divide x minus 3 into this numerator. And we can do that with either long division or synthetic division. So we can write 1x cubed, no x squared, negative 7x minus 6, and we're going to divide by x minus 3. So if you remember synthetic division, you put a 3 up there. And I'm not trying to teach this, I'm just trying to make you remember that you can do this type of thing. So I'm going to go fairly quickly. You bring down the 1, 1 times 3 is 3. You add, you multiply, you add, you multiply, and yes, you get a 0 remainder. So what does this mean? X squared plus 3x plus 2. That's what you get when you divide x minus 3 into that. So I'm going to put that over here, but I can see I can further factor that into x plus 2 times x plus 1. Now we can cancel the x minus 3 factors, and now I can plug it in. If I plug in 3, I get 5 times 4, or 26, or 10/3. So I can see as x approaches 3, from both sides, I'm going to be going to 10/3. So a little bit bigger than 3 up here at 10/3, I've got a hole. So I've really analyzed this quite well. With a little more analysis, we could probably figure out exactly what's going. We just know that we have some type of asymptote. It might do something like that, and it might do something, who knows for sure. I'm just not going to try at this point to analyze it, but it could go something like that. We just know that we could make this continuous. This is a removable discontinuity. So if I wanted to come up with a new function, g of x, that was continuous at x equals 3, I could make this extended function. I could call it h of x when x is not equal to 3, and then I could call it 10/3 when x equals 3. And now this new function would fill in this hole. That might seem like a lot of work to do that, but remember, continuity is going to be pretty important. Okay, so here are 3 separate functions that are all 3 rational functions, and I wonder what's happening there. Well, I'm not going to go through in great detail because we've done problems like this. In all cases, we have polynomials here. So we know that this one is going to be continuous for all, well actually, for all real numbers except for 2. Well, what's happening at x equals 2? We see the numerator is getting close to 4, and the denominator is getting close to 0. So again, we know we're going to have an asymptote. On this problem, when we put in 2 to the numerator, we get 0. We get 8 minus 8 over 2 minus 2 in the denominator. We get 0 over 0. Well, if it was like the last case, we're going to have a hole. But how do we find out for sure? We have to take the limit as x approaches 2. Now, what we get, if we factor the numerator, we can take out a 2x and we can cancel that, and we get 4. So we actually, as x approaches 2, are coming into 4. We know at the graph at the point 2, 4, there's going to be a hole. So that one has a removable discontinuity where we got this indeterminate form 0 over 0. And I hope you're getting some kind of feeling why this is happening. Dividing by 0 makes things big, but you see as x gets close to 2, this number is going to be the same thing as this number. So they kind of cancel each other out, and everything is really just determined by the 2x. Well, let's try one more. On this one, if I plug in 2 to the numerator and 2 to the denominator, I also get 0 over 0. And your first thought might be, oh, we have another hole. But we should try it. Let's see what happens. What's the limit as x approaches 2? Well, we've already factored the numerator before. But now what can we do to the denominator? That's x minus 2 times x minus 2. And yes, we can cancel out these factors, but I still have another factor of x minus 2 that doesn't cancel out. So as x gets close to 2, you're in the same situation you were back here. The numerator is getting close to 4, and the denominator is getting close to 0. So we're going to have an asymptote again. So the reason I made up this example was to show you that yes, usually if you get 0 over 0, we have a hole. always, if you get a number over 0, you get an asymptote. But I wanted to show you this case where we have a double root down here where you still can get an asymptote. So what you really have to learn from that is to check, you have to take the limit as x approaches that value and see what happens. So that really finishes up continuity, and we'll go on to some new things the next time. Thank you.